So yeah, let me get started with the talk today. So today I'll be presenting this topic of Hot Path SSA Form in LLVM. So this was a work that was jointly done by with me along with two UG students, Mohammad Muzammil and Abhay Mishra. Along with that, we were guided by Dr. Avanish Pandey, who was also a PhD student here at IIT Kanpur. He was guided by Dr. Shubhajit Roy. So he's currently working in Qualcomm, India. I'll be presenting this slides today. So, so what we did was that we implemented the Hot Path SSA form inside of LLVM infrastructure. The Hot Path SSA form is based on these two research papers. Like these papers in details discuss the idea behind HPSSA and the implementation in any compiler framework. So we chose LLVM because it's very popular. It's used across the industry and like it has got a huge number of users. So we targeted LLVM. So we already have the static single assignment form, the SSA form. So why did we create another uh, SSA form on top of SSA? The reason for that was if we could do some profile guided optimizations. So if you see the program here, and I mean the control flow graph of a program, I showed two paths, path A, B, D, E, and G. The two paths have been marked in red. They have been shown here. So if we see like along one of the paths on the left, initially all values are set to 0. Over here, if B becomes 9, we can say that A can take a value of 10 along the left path and 1 along the right path. Similarly, C can take a value of 11 and 2. Along with that, Z can now take a value of 110. And over here, D can take a value of 16 or 6, depending which path comes in. But if we consider the values that are possible along the paths that are marked red, then Z takes a constant value of 110 and D takes a constant value of 16. So these red paths could be paths which are frequently executed. In our terminology, we call them hot paths. And we could speculatively say that Z and D are two constants along two different hot paths. And the idea is to like capture this profile information or this summary information in the analysis itself. So in order to first generate these hot paths, so we have to profile the program. We have to come up with some metrics to say what are the hot paths in the program. So for HPSSA construction, what we do is that we use the Boller's acyclic profiling algorithm. This was published in Micro 96. If we take it to more number of paths, there are other papers. These go into the details of how profiling works and how we are able to collect these hot path information. What profile guided analysis helps us to do is that it can give us opportunity to do some kind of code refactoring. Maybe if we have some code that is executed redundantly over some hot path, then or frequently executed path, then in that case we can offload such computations to maybe some other paths. Uh, we can use it for program testing and verification. We can have testing of low frequency paths. These are known as residual paths in the program. So can we profile for residual paths? Can we show properties that hold on some paths and not on the other? The other thing could be we want to do specific profile guided optimizations. Why is profile guided analysis hard in general? Because there are two kinds of information that we are working with. The first is the program information or the program representation. Usually that is through the control flow graph, or you have the AST information, or you have 3 address code information with you. You have some representation of the program with you. Along with that, you have the profiling information, the profiling information tells you like, okay, what are the sequence of basic blocks that are forming a hot path, what is the frequency count and stuff like that. So we generally use a hash table or a map in order to compile these information. So these are two different disparate data structures. So we want some way to unify these representations, and there have been previous work where profile guided optimizations have been used, and these profile informations have been used in compiler passes. So here I show two like papers. The thing is that so they came up with their own representation of what this path profile guided analysis will be. There was a specific paper which did dead code elimination using path profile guided analysis. There was a paper on partial redundancy elimination. They had their own representation of the path profiling, and they had their own analysis written on top of it. So is there some way we can like give a representation which unifies uh, the process of writing these optimization passes? So the objective is that can we weave the profile information into a program representation, into the program representation as a single consistent data structure that provides the convenience of an SSA-like intermediate form, and it also allows for profile guided versions of whatever traditional optimizations that are available in compilers. So with that objective in mind, we came up with HPSSA. The HPSSA form makes PGO very easy. So here I'm showing an example where where we wrote the code for doing speculative sparse conditional constant propagation. So here we were able to, it's like only with this much amount of code, we were able to write a speculative version of the standard SSCP algorithm. Uh, and it like took us very less time to write this code. And as you can see, like this just 35 lines of code and that's it. Um So what is the difference between the normal SSCP and speculative SSCP? So SSCP is a way of like identifying constants in the program. Like I'm not getting into I'll get into the details of what spec SSCP is and how things are in a moment. But as of now, like if you see there are two programs, one on the left and the other on the right. On the left, we have got variables that are marked in pink. These are overdefined. That means these are definitely not constants. We have some variables that have been marked yellow. These are constants in the program that we know through analysis. Say, for example, X, Z, and C, these are constants. N is a constant, so we could directly propagate these values. Now, in case of the speculative form, what happens is that we introduce the notion of speculative constants. These are constants which might be, so as I showed in the very first example, these are constants that are only found in some high frequency paths or more number of executed paths. So on the right hand side, if you see the program on line number 14 and 20, we were able to identify that N and X are also speculative constants. Like X will, like over some hot path, X will always take a value of 7 on line number 20, and N will take a value of 5 on line number 14. So over here, N and X are not speculative constants, but here we could identify them as speculative constants through our profile guided optimization pass. So here I show the LLVM, the control flow graph out of the LLVM IR of the same program. So over here, if you see, like you can ignore the blue lines as of now. I'll go over the blue lines, but as of now, if you can see, we were able to detect that, okay, like this over here, like it has only 5 as the values that are coming to this function. And so the constant value is 5. And over here, both the values are 7. So this variable takes on a value of 7. So these two are the speculative constants. So just highlighting to show these are the two lines I was talking about. So in the standard SSCP pass, like if we are using the LLVM's OPT tool to run SSCP, and we like on some given LLVM program or LLVM IR, then it gives this as the output, where the constants are the ones that are shown on the left. But if we first transform the program into an HPSSA form instead of SSA form, and then we use the speculative version of SSCP, then in that case, we are also able to identify these two constants. So writing out a new pass using using HPSSA is easy. So you have to include our header, and you have to basically call our util to run on the function, and it will give you the function back in HPSSA form. And now that you have the HPSSA form available with you, you can write your own pass on top of the HPSSA form. Okay, so now that we have talked about an example of how HPSSA form can be useful, let's talk a bit about what HPSSA form is. So the traditional SSA form uses five functions as definition mergers. So at the iterated dominance frontiers, you would place these five functions. These five functions would take care of merging the definitions that are coming along different paths, and it will produce a five function like this. In case of HPSSA, what happens is that we use the definition of five, but we have our own definition merger, and this definition merger is happening over frequently executed paths or hot paths. So the very first argument or the very first definition of inside the tau function is the one that comes from the phi function itself. This is the safe interpretation. And the rest of the definitions from x1 to xn, these are speculative versions or speculative interpretations. So if we take a phi over those, it will be along all the hot paths that are coming and joining on that block. So that's the difference between the semantics between the phi function and the tau function that we have inside of HPSSA. So over here, I show an example where we have the program. So I show the frequently executed paths or hot paths here as dotted lines. So these gray dotted lines show the sequence of basic blocks that form the hot path. So if we see in this basic block, we have x5, which is the phi over x2, x3, x4, and x1. Which are all four of these. However, in case of the hot path definition, or in case of tau, we don't have the value of x1 because this edge does not form a part of the hot path. So we are taking the safe interpretation first, which is x5. And then we have the three definitions, x2, x3, and x4 along the three hot paths, and then we are merging those as well into our tau function. So we do the same thing across all the nodes where there is an intersection between the hot and the cold paths. So we have a strategic way of placing these tau functions, the way phi functions are placed. So if the program is in Hot Path SSA form, then each use of the variable is reached by a single definition. This is same as the constraint that comes, or the definition that comes from SSA form. We have the first argument to be the safe interpretation, which is the meet over all paths reaching definition. Along with that, we have the speculative interpretation, which is the meet over frequent paths reaching definition. So this is what supports the profile guided analysis. So if we see over here, and if we try to find, okay, like over the hot paths, what happen? Like, can I say if x2, x3, x4, or is x6 a constant? Like if we try to query those kind of things, then it is the tau function that becomes useful here. So coming back to the speculative SSCP form, so the difference between, I mean, the difference from standard constant propagation is that in case of constant propagation, you would only have the bottom, top, and the constants here. So I am showing the lattice that is used for the data flow analysis in case of speculative SSCP. So in case of speculative SSCP, we introduce new speculative constants. These are variables. These are constants that are marked with the S sign on top. So 1s, 2s, 3s, 4s. These are speculative constants. So if we have an operation between a speculative constant and some other constant, then that constant becomes a speculative constant. So by speculative, we mean that maybe over this hot path, it is a constant. So it may not be a constant over all paths. Then we modify the regular transfer function for tau definition. In that case, what happens is that if so, either we get back top saying that we don't know, it's overdefined, or it is a regular constant, or it is a speculative constant. So we get those as the like output from the mean. So all the speculative variants of your data flow analysis could be treated in the similar way. You just have to add this new lattice elements in your lattice, and you have to like modify the join operation for the tau function. Like that's the thing that is required. So how did we construct the HPSSA form? So the tau functions, like similar to phi functions that are inserted in the iterated dominance frontier, these are inserted at iterated thermal frontiers. So thermal frontiers are nodes where a hot path and a cold path, they are merging, and we allocate arguments to tau. So we do a path sensitive traversal over the program to identify like which definitions are flowing over which hot path, and we order the definitions accordingly. The first definition being the phi definition that is there in that basic block. So over here, like if we want to transform out of the HPSSA form, in that case, like we can do that over the optimized version of SSA as well, because so for us, like I mean, even the optimized SSA form, which breaks the phi congruence property, HPSSA can still work on that. How did we implement HPSSA? Well, we added an LLVM intrinsic signature, LLVM tau, inside the LLVM intrinsic std file, saying that this will be a new kind of a pseudo function, which will be supporting addition and removal of tau functions. Along with that, we modified the verify dominate users function because we did not want to treat LLVM. So we did not want LLVM to treat tau functions as regular functions because these would never be like used directly to generate code. So these will only be used in optimizations, and when optimizations are over, you can convert your HPSSA form program into the regular LLVM SSA form. So I'll discuss how the reversal happens or how the removal of HPSSA happens. So we have this HPSSA class. We provide you with a run function, which you will have to invoke with first in order to run your function or your example, convert it from SSA to HPSSA form. So we used so in order to like track what are the hot paths that are there, we used the LLVM vector data structure. We used this map from basic blocks to bit vector or the hot path set in order to track what are the hot paths that pass through a given basic block. We use this to keep the hot definitions of the variable that reach a particular basic block across a particular hot path. And we used a renaming stack in order to store the most recent tau definition that have been encountered. And to be later replaced. So if we are doing a variable renaming, which is a same thing that is done in case of in case of SSA as well. So we are using this renaming stack to make sure that we are able to like replace the users with tau variable. And finally, we have the allocate args function that handles how we are assigning the arguments to our tau function, or like what are the definitions that are reaching a particular tau function. So if we want to come out of the HPSSA form, then in that case, we have to run the tau destruction pass. So we have this there inside of HPSSA implementation itself. So if we have a function like this, if you see on to the left, if we have x3, which is the tau over x0, x1, and x2, then in that case, we can go back to the use of only the only the safe interpretation, which is the very first variable. So we say that x3 is equal to x0, and everything else remains the same. So with that, I would like to conclude. So a Hot Path SSA gives you the flexibility and the avenue to write your own profile guided optimization passes. So without worrying as to like how to deal with that profiling information separately. So you get the tau functions. You basically write your analysis using the definition that are there in the tau functions, and we are soon planning to open source this work, and we're trying to push it into the LLVM's main branch. So the first thing that we are trying to do is to pass the profiler. Since we have an implementation of the Boiler's profiler, so first we want to put it into LLVM, and once that is approved, we'll probably add the HPSSA form as well as a pass in OPD. So this is the GitHub repo. So thank you. Thanks a lot for listening. I'm open to questions that are coming up.
Sumit, I have a question. So, were you able to implement any other passes other than the SCCP pass on top of HPSSA?
So we have not tried that out yet, but I think yes. I mean, it's implementable. Like we'll have to basically change the meat and the other definitions that are being used. So like as long as we can do that, we can definitely like write out other passes in HPSS. Yes. Yeah.
Okay. I think Abhishek has a question.
Uh, Hello.
Yeah, hi,
Hello.
Abhishek. We can hear you.
Uh, like, Sorry if this is too basic, but what do you consider a hot path? Like, what percentage is should be the
So
branch taken?
So while we are basically profiling the program, so what we try to do is that uh, so for us it was the top most frequently executed paths that are there in the program. So that is what we call as hot paths. So maybe like in the examples which I had shown, like maybe there are a sequence of basic blocks that are iterated the most number of times, like no matter what the huge array of inputs that you start with, like there is a sequence of paths that are executed maybe 5,000 times, and there are some paths that are executed maybe 20, 30 times. So the paths that are executed beyond certain thresholds, we can consider them to be hot paths, and we can run our analysis on those hot paths. So
So,
although so this definition of what a hot path is something that's depending on like how you want to profile things. like how you want to profile your paths, like on what criteria do you want to like say that okay something is a hot path. So this is something that you can decide, and you can maybe say that instead of the most executed paths being the hot paths, maybe the least executed paths are the hot paths. So in that case, you will have much more number of paths to work with in order to work your analysis. Yeah.
So Abhash has a question.
Hello, can you hear me?
Yes. Yes. Yeah.
So when you convert from the SSA form to HPSSA form, what's the time complexity of that algorithm when you're converting from one form to the other?
I think I don't recollect it right now, but uh, I think I don't. I'm not able to recollect it right now.
But it is fast, right? That is
Yes,
what
yeah.
I was.
I
Yeah.
mean, at least I'm not able to recollect the exact time complexity, like in terms of like the number of definitions and like edges that we have in the program. But like even if you think about the like the LLVM, like the LLVM translation, like I mean the times that you have, in that case, like we were able to convert some large programs into SSA form, and we were able to like run our analysis quite quickly. Yeah.
Okay, okay. Thanks. I have one more question. Uh,
Yeah.
let's say you have done the speculative SCCP,
Yep.
and so you have that means you have renamed the like put the constant at the right places, right? And
Yes.
what if the hot path is not taken? How do you recover in that case?
So yeah. So I mean, when you are converting this to like the like machine code which is getting executed at that point of time, you will not have the speculative like constants or like those definitions will not be available at that point of time. But if you are like if you are maybe like relying like or you in some sense if you are just considering the hot paths for some other analysis, and if you want to see the constants that are there on those hot paths, only then like this thing makes sense.
Okay, okay, yes,
So
yes.
yeah, yeah,
Thank you.
yeah.
Yeah, Manasis has a question. Yeah, please go ahead.
I so some of the most impactful optimizations in profile guided optimizations in LLVM involve reordering blocks or moving code around in general. Do you see HPSSA being able to help those kinds of optimizations?
Uh, I I think it would be possible. I think it would be possible in cases where like maybe if we could like speculate out constants, then maybe we could like host them like up, or we can move them to some other place. So I mean, so you could run transformation passes along also on the HPSSA form using the tau functions. You can write transformation passes as well. So although we have not directly explored that, we have explored more like traditional like data flow analysis frameworks. But if there is some kind of code motion or we are rearranging blocks, yeah, I think that can also be done.
So I mean, maybe let me add to that. So there are so whenever you're doing an optimization, there are two parts to it, right? First part is doing an analysis, which says that what is that you want to do. Like for example, even if you're talking about code motion, maybe even if you're talking about something like PRE, right? So you'll have to figure out what are the partially redundant expressions that you would like to move around. So that is where HPSSA can really help. And after that, there is a transformation wherein really move them around, right? So that is what would be exactly what you would have otherwise done, right? But where HPSSA really helps you is in identifying, basically doing this analysis, which tells you that okay, these are the partially redundant expressions. In this case, we can talk about, let's say, the speculative partially redundant expressions, and then you can decide how to move them around, right? So that is the second part. So the second part remains the same no matter like after you have done the analysis, the transformation pass would exactly remain the same what it was earlier. It's only where you're doing the analysis HPS will really help you identify expressions which are speculatively true, which may not hold at all times, but would most likely hold in most of the cases.
Okay, yeah, that answers my question pretty well. Thank you.
Sure. Thanks.
Yeah, I think a follow-up question is that so when you do a transformation, so at some point you'll probably violate the HPSSA form, right? Do you provide? Do you still have to run the analysis pass on top of that again when you do another transformation pass?
Yeah, so it will be very similar to the case what happens with SSA. So, so you have to be careful with the transformation. So if you keep the phi functions or the tau functions intact, you can still manage to keep the SSA constraints going. So you may not still break them. So you should not be moving the tau functions or the phi functions, which are basically basically holding the definitions together. But again, I mean, this is a very good question. So I think we really did not try out any code motion optimization yet. So yeah, but yeah, I mean, I can see where you may have problems, but it can be handled. This is the same as would be the case with SSA. So whenever you are doing SSA transformation, you have to be careful about the definitions, right? So you have to be careful about where your fees are. So in this case, you have to take care of both your fees and your taus. That is what changes.
Right. I think the line of thought I'm coming from is that when you do a simplified CFG on a speculative call or on a speculative value, you might try to remove a sequence of basic locks, right, along a hot path, and then you'll all of your I mean, there can be chances that your fees and your taus can be invalid along that path, right?
Yeah, so what you would do is that you will remove the other statements, but you will still preserve the blocks with the tau statements. And then you will collapse the taus. So you'll run a simplification pass, which will collapse the multiple taus into a single tau eventually. So you have to do it in multiple phases so that HPSSA constraints remain valid.
Okay. Yeah. Thank you.
Yeah.
So, yes, and
Another
again,
kind of an engineering question. Okay, so sorry, go ahead.
yeah, so I mean, just to add to that is that in case if you are removing some tau functions or tau definitions, then and even if you're collapsing like taus, you'll have to make sure that you are using this replace the users and you remove the variables like accordingly in the same order. Like otherwise, there can be some transformation. Yes, go ahead. I think there was a question.
Oh, yeah. So it's kind of a engineering question, so it might not really be too relevant. So does anything change if you do instrumentation profiling versus sampling-based profiling, or does everything remain exactly the same?
Oh, that's a great question. That's a great question. So so there are two parts to it, right? First is the estimating the profiles, right? So the sampling based profiles are extremely low overhead, so you can do them very fast, but of course the estimates may not be very good, right? On the other hand, the instrumentation based techniques have significantly large overheads. So something like uh, I mean, path profiles have something like 20 to 30% overhead, depending on what are the data structures you're using. So there the estimates, the profile estimates you'll get will be exact. I mean, so there is no approximation, there is no estimation there. So again, it is your choice. So how much overhead you can tolerate, and depending on that, you will decide your profiling technique. So we do not advocate what profiling technique you use. All we need is that you tell us what the profile information is, no matter how you collected them. Did you use a sampling based technique or did you use an instrumentation based technique? Doesn't matter. We do not care about it. So our tool will take these histograms of a path profile information, take the source code and it can convert it into HPSSA. So it is up to you to decide what you want to do. And again, there was this the other question. I'll just add to that. Like again, like we do call it hot path SSA, but then they don't have to be the hot paths. They could have been the cold paths, could have been the low frequency paths. Like for example, if I'm doing program testing, then I might want to do something called residual testing. Residual testing means that I want to test paths that I have not tested so far. Right? I want to discover new paths that I have not seen so far. So there it might be advantageous to look at paths which are executed very with a very low frequency. They hardly get executed. I want to really push them more, right? So essentially when we are building this hot path SSA, it doesn't matter what your semantics of these selected paths are. So you give us a set of paths and you say that these are the paths I would like to track, and you give us the source code, and we will give you the hot path SSA which tracks these selected paths that you've given us. That is what this form will do for you. And the use case is completely yours. You can decide what you want to do with this.